When discussing electrons around an atom, normally the subject matter turns to things like electron configuration, orbital notation, things like that, and it's easy to get your eyes away from the prize. I'd like to bring us back to some good solid concepts, notably that of electron dot structures and valence. You can learn a lot about chemical behavior without going any further than that. Electron dot structures simply show the outermost shell of electrons. Why? They are responsible by and large for chemical reactivity. Generally speaking, within them, especially for the elements of life, the atoms have fully filled inner shells. So let's take a look at the outer shells. Neon, which is right here, has all 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 in the second shell. This is a happy camper. It's a very stable element, and it's a good model for showing the ones that aren't. Lithium, for example, has simply, here it is right here, only 1 electron in that second shell, and it's a notoriously reactive species. It will do nearly anything it can to remove it. Beryllium, for example, has 2 electrons in that second shell, but it would be a mistake to draw them like that. Don't forget about Hund's rule. Spread them out when you can, and beryllium typically forms, as for the entire second column, 2 bonds. Let's do hydrogen, oxygen, nitrogen, and carbon. That is what you're mostly made out of. These are the elements of life, and honk if you love chemistry. You should come up with hydrogen, oxygen, don't forget to spread them out, nitrogen, and carbon. The utility of this can be easily recognized when you realize that hydrogen forms 1 bond, oxygen 2, see these 2 lone campers? Nitrogen 3, and carbon 4. What a powerful tool. So valence electrons are really the key to understanding chemical reactivity, and this can be shown in the periodic table. Let's take one brief aside and take a look at diamagnetism and paramagnetism. Diamagnetism arises when you have paired electrons, like right here or right here. This results in a weak magnetic repulsion. Paramagnetism can result in either a weak magnetic attraction or a very strong if they're what they call ferromagnetic. In any case, you have unpaired electrons. For example, carbon has unpaired electrons. And if it's quite strong, as the case with iron, cobalt, neodymium, nickel, are the common ferromagnetic elements, and they can result in a very powerful magnetic attraction. This being a chemistry course, I'm not going to go any further discussing magnetism, however. I do want to take a nice look at valence, however, because the periodic table is designed to show, if it can show one thing, it's designed to show the valence electrons. They're arranged by column, not by row, but by column. So if you have 1 valence electron, you are unstable. 2, also unstable. Since the elements fill up out of order somewhat, meaning that it's not going from first shell to second shell to third, but rather you can start to fill within, and the possibility of unfilled inner shells is a distinct occurrence, the transition metals will always have only 2 valence electrons. I mean, consider any one of them. Scandium, 4s2, 3d1. The highest electron in terms of energy is that 3d1, but you do have electrons in your 4th shell. This leads to somewhat complex behavior, and that you can have multiple charges for any of these elements, with some notable exception. For example, people refer to this diagonal, aluminum, zinc, and silver, as always being +3, +2, and +1. Working our way over to the p group, we see that we have 3 valence electrons. It will lose 3. 4, it will tend to share, since you're right in between 0 and 8. And 5 valence electrons, it's easier to gain 3 than it is to lose 5, so you tend to gain 3 electrons and form a -3 charge. Oxygen group will gain 2, the halogens will tend to gain 1, and the noble gases will tend to do nothing at all. That simple relationship between valence electrons and reactivity describes such a large percentage of all chemical behavior. And that is a look at electron dot structures and valence.